All right, this video is going to cover the last section that we have from Chapter 5. As you know, in Chapter 5, we've been looking at a bunch of different types of tests for determining if a series converges or diverges. And in this last section, we're going to take a look at two more tests. We have the ratio test and the root test, and they're going to be used for some different types of series that we haven't seen yet. So let's jump in this video to talking about the ratio test. We'll do one more video where we'll talk about the root test. So Theorem 5.16 from your text discusses the ratio test. And the first thing I want to do before we get into that theorem is I just want to say when we would typically use a ratio test. And this one's actually used quite often. There's really two main scenarios, though. The first one where we're going to want to do this is anytime, a lot of times we have factorials in our series. Remember what a factorial is. It's something like 5 with an apostrophe after it. That means 5 factorial. And then the other thing is when we have constants raised to the nth power. So either one of those scenarios, like this could be like 5 to the n, for example, we're going to want to use the ratio test. A lot of times we have both factorials and constants raised to the nth power. Now, if you remember, let's do a quick review of factorials. Review of factorials. If you don't remember, like 5 factorial is going to mean 5 times 4 times 3 times 2 times 1. So whatever that comes out to. 5 times 4 is 20. You multiply 20 times 3, you get 60. Times 2 is 120. 2 factorial, likewise, would be 2 times 1, or 2. 1 factorial would be just 1. And then the kind of oddball is 0 factorial. 0 factorial is also defined as 1. So if we had n factorial, n is a constant, we don't know what it is, then what we're going to have is we're going to have n times 1 smaller than n times 1 smaller than that times ... times 3 times 2 times 1. So we're going to keep whatever n happens to be, we're going to keep multiplying numbers 1 smaller than the previous number all the way until we get to 1. So here's what we do. You have a ratio test that has, and you're going to use it again when you have factorials or constants raised to the nth power. And what we're going to do is we're going to calculate the limit of the absolute value of the ratio of a to the n plus 1 over a to the n. And depending on what this limit is equal to, that limit is equal to rho. If rho is less than 1, then it converges absolutely. If rho is greater than 1, then the series diverges. And if it's equal to 1, we don't have, it's inconclusive. The test is inconclusive. Inconclusive. Okay, so let's see how this works. Example 1, determine if the series is convergent or divergent. And so we're going to use the ratio test, and we want to find rho. We want to find the limit as n approaches infinity of a to the n plus 1. So that's our n factorial over 5 to the n, where instead of having n, we have n plus 1. So this is going to look like n plus 1 factorial over 5 to the n plus 1. And then that's divided by a to the n, which is n factorial over 5 to the n. Now here's the thing. So we could write it out like this every time, but I like to save writing time, I like to skip this step and jump straight to the next step. So, because instead of dividing two fractions, we could multiply by the reciprocal of the second fraction. So it's much easier for our math if we just write it like this the first time. So we take the top fraction, n plus 1 factorial, over 5 to the n plus 1, and then we multiply that by the reciprocal of the bottom fraction. So that's going to be 5 to the n over n factorial. Again, that's just taking this bottom fraction and taking its reciprocal. So we have that. And looking at this, we now need to be able to simplify what's inside this product of two fractions so that we can get down to something simpler. So let's do some work on the side. So if we take a look at n plus 1 factorial, what is that going to represent? Well, that's n plus 1 times n, right? One smaller than that, times, and you keep going all the way till you get to 1. So really, everything after n plus 1, so if we look at n plus 1, what we have below here is we have n times every number smaller than it, every whole number smaller than it. So the n times ... all the way to 1, that's the same as n factorial. So we can say that n plus 1 factorial is equal to n plus 1 times n factorial. We also want to simplify down 5 to the n plus 1 using the product rule for exponents. So we know that 5 to the n plus 1 is the same as 5 to the n times 5 to the 1, or just 5. All right, so we can now simplify our expression for rho quite a bit. We have the limit as n approaches infinity. And that first fraction we can rewrite, as we just saw, as n plus 1 times n factorial. And then in the denominator, instead of 5 to the n plus 1, we can rewrite that as 5 to the n times 5. Then we have 5 to the n over n factorial. And now, hopefully you can see, there's a lot of things that we can cancel. So we have n factorials will divide out, and we have 5 to the n's that divide out. So what we're left with is the limit as n approaches infinity of the absolute value of n plus 1 over 5. And if we let n approach infinity, this is going to basically be infinity on the top over 5, which is infinity. So rho is infinity. And remember, we're comparing rho to 1. And in this case, infinity is going to be greater than 1, which means the series diverges. So we got to make our statement just like we have all along in chapter 5. So series of n factorial over 5 to the n diverges by what test? By the ratio test. Diverges. All right, so that's the first one. We're going to do a couple more examples. So let's go ahead and move to the next page. We have part B of example 1. And so we're going to do the same thing, except I'm going to start this one out by writing it, by skipping that first step. So we have the absolute value, and we do n plus 1 first. We have negative 10 to the n plus 1 over 4 to the 2 times n plus 1 plus 1 times n plus 1 plus 1. So notice everywhere where we had an n, I plugged in n plus 1. Then we have times the reciprocal of the original. So we have 4 to the 2n plus 1 times n plus 1 over negative 10 to the n. Okay, and now we need to, it's just algebra, just kind of like the last one. So we can do some rewriting here, and I did notice that I left off the limit at the beginning of this. That is important. We got to make sure we have that. So we have rho equals the limit as n approaches infinity. And so we have we have the limit as n approaches infinity, we have, using the product rule, we have negative 10 to the n times negative 10 in the numerator. And then in the denominator, we're going to have 4. And if we distribute that 2, we have 2n plus 2 plus 1. So that's going to be 2n plus 3, right? So we have 2 times n plus 1 plus 1. That's 2n plus 2 plus 1. It's 2n plus 3. And then we have n plus 1 is n plus 2. All right. And we have 4 to the 2n plus 1 times n plus 1 over negative 10 to the n. And initially, we can see the negative 10 to the n's are going to cancel. Now, what do we get when we divide 4 to the 2n plus 1 over 4 to the 2n plus 3? Well, remember, we're going to subtract the powers. So when you subtract the powers, you're going to end up with 2n plus 1 minus 2n plus 3. And that's going to give you, the 2n's will cancel. That's going to give you negative 2. So this is going to give you 4 to the negative 2, which is really 1 over 4 squared. 1 over 4 squared. So simplifying this, we can continue. We have this is equal to the limit, as n approaches infinity, of negative 10. We have n plus 1 also on the top. And then remember the 4 to the 2n plus 1 over 4 to the 2n plus 3, those simplify to 4 to the second in the denominator. 4 to the second over n plus 2. So we're almost done here. This is the limit as n approaches infinity. Now actually, we have the absolute, we have constants here. So we have the absolute value of negative 10 over 16, basically. And we also have the absolute value of n plus 1 over n plus 2. And that initial, that first part, the absolute value of 10 over 16, that just becomes 10 over 16, or also, what is that, 5 out of 8? So we have 5/8. This is going to go to 5/8. The absolute value of it turns it positive, times the limit as n approaches infinity of n plus 1 over n plus 2. And remember, we talked about previously in this chapter that when you have a limit like this, where you have, you just look at the exponent or the coefficients in front of your highest powers of n. So this is 1n and 1n. So the limit of that is just going to be 1 over 1. It's just going to be 1. You could also use L'Hopital's rule as well, but we don't have to. This is 5/8 times 1, or 5/8. And then again, we're comparing it to 1. And in this case, we're going to be less than 1, which means we're going to be what? According to the ratio test, that means when we're less than 1, we're going to converge absolutely. So our series converges absolutely by the ratio test. So that's part B. We've now seen one that converges, one that diverges. Let's look at one more here, example C. And This one doesn't. So the first one had a factorial in it and a constant to the nth power. The next one had a constant to the nth power. A couple of them actually, right? 4 to the 2n plus 1 and negative 10 to the n. This one doesn't really have a constant raised to the nth power. And just looking at it right off the bat, I'm looking at it and I'm going, remember, one of the first things we always want to do is do the divergence test. Divergence test, just looking at it, if I take the limit as n approaches infinity of n plus 2 over 2n plus 7, what does that equal? Well, just looking at those coefficients, we have 1n over 2n. This is going to be 1/2. And that is some constant that's not 0. That means if all the terms are approaching 1/2, that means for our sum, we're just going to keep adding 1/2, remember? So what does that tell us about the series? It tells us it diverges. So our series diverges by the divergence test. If we were to actually use the ratio test, we would see that it would be what? Well, what would we get for that if we tried that? So if we tried to find rho by taking the limit as n approaches infinity, we would have n plus 1 plus 2 over 2 times n plus 1 plus 7 times 2n plus 7 over n plus 2. And this can be simplified. So n plus 1 plus 2 is going to be n plus 3 over, and then on the bottom we have 2n plus 2 plus 7, so that's what, 2n plus 9 times 2n plus 7 over n plus 2. And this particular one, we could multiply this out. So on the top we have n plus 3 multiplied by 2n plus 7. That's going to be 2n squared plus 7n plus 6n, so that's plus 13n plus 21. And then in the denominator we have 2n squared. If we multiply this out, 2n squared plus 4n plus 2n, so that's plus 9n. So we have 4n plus 9n is 13n plus 18. And we have a limit as n approaches infinity. Again, we're just going to look at those coefficients in front of our n squared terms. So we get 2 over 2, which is 1. This is 2 over 2, this limit, which is 1, which according to our ratio test, it's inconclusive. Can't do anything with this. So had we started with that, it wouldn't have gotten us anywhere. So you always want to keep in mind problems where it looks like we would be able to take advantage of using the divergence test. Okay, that's going to do it for this video. We'll do one more video for this section to cover the root test. I'll see you in the next video. Thank you.